So, let us look at this map A 2 A mod I 1 cross A mod I 2. So, if I 1 plus I 2 is A, then I 1 I 2 is same as I 1 intersection I 2, and we said phi is so this is the natural map phi is surjective if and only if they are co-prime, and then third point that we said phi is injective if and only if is 0. Right. Now, this can be stated, all these results are stated for n ideals. So, the proof is kind of similar, I will not go into the proof, but the statements are, so let I 1 up to I n be ideals, and we have this map phi from A to A mod I 1 cross A mod I n. Then for all I not equal to j, I plus I j is A. This would imply that product I from 1 to n I, this is same as intersection I from 1 to n. Okay. Phi is surjective if and only if I and I j are co-prime for all I not equal to j, and phi is injective if and only if this is intersection I is this is 0. The last point is pretty straightforward, because it's the kernel is the intersection. The other ones are also I mean this is pretty similar to the proof that we gave. So, I will leave the proof as exercise to you. So, we have seen that the ideals, we have seen lot of basic properties of these ideals. Now, suppose you have two ideals I 1 and I 2, we have already seen that this is not an ideal in general, okay. But suppose you have, this is a prime ideal, these two are prime ideals. Yeah. So, the question is, if I have an ideal which is contained in the union of two ideals, if it is there in the, okay, yeah, can we say that it is indeed, so in the integers as we saw now, in the integers if I take an ideal, this is if it is contained in the union, it is contained either in, either here or here. But is this always true? So, to start with, let us look at an ideal I contained in union of two prime ideals. Suppose I is contained in P1 union P2. Can we say that I is, of course this is not an ideal. Can we say that I1 is contained in P1 or I is contained in P2? Let us see if this is true. So, let us start with an element x. Yeah, any doubt? Let x be an element in I. Okay. So, we want to say that it is either, we want to check whether it is here, whether this is true or this is true. Suppose this is not true, okay. I want to say that then this has to be true. For this to hold, if I say this is not true, then I have to say that this is true. So, let us assume I is not, that I is not in prime P1. What does this mean? This means that there exists an element, there exists some y in I but not in P1, right. Now, y is in I but not in P1. Can you say something more about y then? Y is here but not here. See, to begin with, this is there in the I is contained in the union. Therefore, y has to be in P2. Our aim is to check whether x belongs to P2. Okay. So, let's look at the element x plus y. What can you say about x plus y? This is in I, right. The element x plus y is in I, therefore, it is either in P1 or in P2. Can it be in P1? Suppose it is in P1. What does that say? Can we get a contradiction? X is in I. X may be in P1 or may not be in P1.
You will get contradiction that y is in P1. If x is in P1.
So, if x is in P1, that will imply that y is in P1. Okay. So, suppose if x is in P1, then this would imply that x plus y, yeah, suppose x plus y belongs to P1, then x plus y is in P1 and x plus y belongs to P1, so x plus y minus x belongs to P1, which means y belongs to P1. That is a contradiction. Therefore, x does not belong to P1. X is in I and x does not belong to P1. Where can it be? So, this implies that x has to be in P2, and that is exactly what we were trying to prove. So, we have started with an arbitrary element of I and proved that it is in P2. So, this implies that I is contained in P2. So, what did we prove now? So, let P1 and P2 are prime ideals, be prime ideals. If I is an ideal such that I is contained in P1 union P2, then I is contained in P1 or I is contained in P2.
So you assume that x plus y inside P1.
Ah, okay, good. So, let us complete the proof. So, suppose x plus y is not in P1, then where can it be? Then x plus y is in P2. So, therefore, x plus y minus y belongs to P2. This implies x belongs to P2. Right? Yeah.
Means I is always contained.
Sorry? If, so what is the assumption that we have made? If I is not contained in P1, it has to be in P2.
So, sir, where you use the property of prime ideal?
Because so in the case of two ideals, we are not really using the property of prime, are we? We are not. Yeah. So, if this is I is contained in two ideals, it has to be in one of them. That is what we are proving. Good observation. Now, so therefore, it is natural to ask whether we can extend this for any finitely many ideals. So, the question is, suppose I is contained in I1 union I2, then can we say that it is contained in one of them? Yeah.
Sir, are we not using the property of prime and saying that x plus y will belong to 1?
No. We are when do you say a ideal is prime?
Sir, y is in P2.
Yes.
Imply that y is in I also.
No, because y is See, we have started with y in I, but in general y is in P2 does not mean that it is in I, because it is in the I is contained in the union. So, let's go ahead and try to prove in the same manner. Let us see what happens. Start with a element. So, let us assume this is true for the case of n minus 1 ideals. We have proved for 2. So, if I take, if I is contained in a collection of n minus 1 ideals, then it is contained in one of them. Let us assume that. Okay. So, assume that if I is contained in, we did not use the property of prime in this. So, let us not assume it for the time being and see whether we need it at some point of time. If we do not need it, we will prove the general case. If we need it, we will impose the condition and prove it. So, assume that if I is contained in I1 union I n minus 1. So, here the induction hypothesis is not just I1 union I2, I mean you should not confuse with the notation. If the induction hypothesis is, if I is contained in any n minus 1 union, then it is contained in one of them. So, I am just denoting it by I1 up to I n minus 1. If I take a collection of n ideals, this should be, the induction hypothesis should be true for any n minus 1 collection, I2 up to In, I1, I3 up to In. Okay. So, then I is contained in so now let us assume, let I be contained in I1 In. Again by induction hypothesis, if I is contained in any n minus 1 ideals, union of n minus 1 ideals, then we are through. If I is contained in, so I will just use the notation like this, I1 union I n minus 1, then by induction I is contained in one of them. So, therefore, we can assume that I is not contained in any n minus 1 collection. Okay. So, therefore, assume that I is not a subset of I1 I n minus 1 for this I1 up to I n minus 1 contained in, you take any n minus 1 of them, I cannot be contained there, because if I is contained there, then we are through by induction hypothesis. So, therefore, we assume that this is not true. So, now let us choose an element, let xi be an element in I, but not in the union of, so ij j from 1 to n, j not equal to I. That means x1 is in I, but not in I2, I3 up to In. I is not contained in this union, right? For any I, this is not, I is not contained here. That means there exists an element here but not in this one. So x1 is in not in J for all j not equal to 1, x2 is not in J for all j not equal to 2, and so on. I am choosing elements like this. Okay. So let us assume that, you know, let us assume that I is not contained in ij, j from 1 to n minus 1. See, my aim is to show that I is contained in one of them. So let us assume it is not in the first n minus 1 ideals, and I want to show that, I want to see whether I is contained in In. Now here we want to again, you know, use this trick of creating an element in I, but it is not in other, you know, ideals. So if I take x1 up to x1 plus x2 up to xn, what can you say about this element? This belongs to I certainly. But then we are starting, see, we want to say that I is contained in In. Okay. So let's start with this. We will try to prove by contradiction. Suppose this is not in any one of them. Let us see if we get a contradiction. Okay. So x1 up to xn, this is in I. Okay. So what? So it has to be in one of them, right? I is contained in the union, it has to be in one of them. That means x1 plus etc. up to xn is in one of the ij's. Now xj belongs here, so I can remove that. x1 x2 up to xj minus 1 plus xj plus 1 up to xn belongs to ij. From there we cannot proceed. See, there were only 2. So therefore when we remove 1, there was only 1 remaining and we could conclude. But here we have more than 2. So therefore, say if this is, for example, if this is 1, that would imply that x2 up to xn belongs to I1. So what? So we have to modify the proof. The same proof does not work. So therefore here comes a small trick. Suppose I look at this element x1 up to xn minus 1. Look at this product. Can we say something about this product? This is there in I1, this is there in, it is there in P1, it is there, I mean I1, it is there in I2, it is there in In minus 1. Can we say it is there in In or not? x1
Action belongs to N.
x1 belongs to I1 but not in anything else, x2 belongs to I2 but not in any of them. Okay. So, this product we cannot say anything about whether it belongs to In or not. Now, suppose my all these ij's are prime, then can we say something about whether this element belongs to In or not? Suppose your In is prime, does this belong to In? Because none of them belongs to In. Therefore, this cannot belong to In. So, if I is a prime ideal, if Ij or In is a prime ideal, then x1 up to xn minus 1 does not belong to In. Similarly, if I1 is a prime ideal, x2 up to xn will not belong to I1. If I2 is a prime ideal, x1, x3 up to xn will not belong to I2. So, therefore, I look at this product. Now, consider the element y equal to x2 up to xn plus x1, x3, x4 up to xn, x1 up to xn minus 1. So, from each product I remove the corresponding ith element. Is this element in I? It is there in I, right? This will say that y is in I. I is contained in the union. Now, in which ideal this will belong to? This implies y is in Ij for some j. Now, let us come back to this product. Just for understanding purpose, suppose this is in I1. Okay. Now, is this portion belong to I1, assuming I1 is prime? Will this component belong to I1? What about this component? All the rest will be in I1. So, therefore, if y is in I1, y minus this portion will be in I1, that will imply this is in I1, but that is where we need the assumption on primes. Okay. So, then so this imply y is in Ij for some Ij, yeah. So, this will imply that x1 up to xj minus 1, xj plus 1 up to xn belongs to Ij. If Ij is prime, is a prime ideal, then this is a contradiction. Okay. So, what did we prove? If I is contained in a union of prime ideals, then it has to be in one of them, right? Is that clear? No? If all I1 up to In, all of them are prime ideals, then I has to be in one of them. Okay. So, therefore, we proved if P1 up to Pn are prime ideals and I is an ideal such that I is contained in P1 Pn, then I is contained in Pi So, how did we prove this? We used induction. For n equal to 2 we have proved it. Suppose n is bigger than 2, then if I is contained in any of the n minus 1 primes, then by induction we are through. So, therefore, we can assume that I is not contained in any n minus 1 collection. We want to say that I is contained in one of them. Suppose not. Suppose I is not contained in any one of them, then we choose an element which is in one of the primes, but not in any other n minus 1. We can do this by again the assumption that I is not contained in any n minus 1 collection, union of any n minus 1 collection. So, I have x1 x2 up to xn, then I form an element in I by taking a product avoiding one of them, taking an n minus 1 product, all the n minus 1 products of x1 up to xn minus 1, sum them up. This cannot be in any of the prime ideals, because the ideal is prime, all the ideals that we are considering are prime. That is the idea of the proof. Okay?
Sir,
Yes.
how do you use the fact I is not contained in ij for all the
So, this is ij is not contained in j, yeah. Where did we use it?
We are just proving by previous using the previous result.
No, y is in I. Sorry, we are in we are using this we are only using to say that x we can choose elements which are not in n minus 1 of them. Are we using only that much? So, let us go through the proof again. I start with xi, which is here, but not in any one of them. Therefore, y is in I, therefore, y is in ij for some j. Therefore, x1 up to xj minus 1, xj plus 1 up to xn belongs to ij. If ij is prime, this is a contradiction.
If we did not take that, then we can't do the product.
No. See, we have to. No. See, what is our assumption? I mean, this is, we are getting a contradiction to this assumption ultimately. See, if we are through if I is contained in one of them. That is what we are trying to prove. I mean, the proof we don't really have to do anything if I is contained in any one of them.
So
Yeah.
So we are not using this fact that I is not contained in any of the
No,
ij.
we are using that because if I was contained in ij, we cannot.
Yeah, we cannot choose. We cannot choose
order.
xj, right? Xj minus 1. For example, if I is contained in ij for some j, we cannot choose xj. Not xj, anything other than xj. Anything other than xj. Or is it, sorry. If I is contained in ij, you look at this union. Yeah, I from 1 to n, I not equal to j, sorry, except j. So this is so no, I want to say I equal to j is always there. So take for example, let us take j equal to 1, and if you take I from 1 to n minus 1, I cannot choose an element here because when I take I without this, it is already empty. I is contained in I1, so I cannot choose an element here. I mean this comes from the assumption that I is not contained in any n minus 1 union. It is a byproduct of that assumption.
So here you uses the fact y belongs to I implies y belongs to ij for some j.
Sorry?
Y belongs to I implies y belongs to ij for some j.
That's from the initial hypothesis that I is, that's not in any of the assumptions. This is the hypothesis that I is contained in the union of n ideals.
This is true for each element, but we are proving that this is also true for the whole idea.
See, this is the hypothesis. What is our hypothesis? I is contained in union of n ideals. So if I take any element in this, it is in this, which means it is in one of them. That is the hypothesis. Later once that this is an assumption in the proof. This is also an assumption in the proof, but that follows from here. That is a byproduct of this one. So is this clear? Now let us look at, now what happens to the, another possibility of these union intersection. Suppose a prime ideal is contained in the intersection. You have a prime ideal contained in the intersection. Can we say it is in one of them? Does that imply P is contained in, again it is the, this is contained I1 or P is contained in I2. Again prime ideal, and this is true for any ideal. Okay, so let us look at the other possibility. P contains intersection. So I have two ideals, their intersection. It is contained in a prime ideal. Can we say I1 and I2, one of them is in P? So this is not obvious. It does not have a obvious answer, looks like. Yeah, so let us see, at least in the case of, when we think about this, in the case of integers, this is, right? Integers, this is same as the product. sorry, this same as the taking the LCM. LCM is contained in P means LCM is divisible by a prime means one of them has to be divisible by the prime ideal, therefore it is the prime integer. So therefore let us try. So let us start with, we want to check whether I1 is contained in P or I2 is contained in P. So let us assume I1 is not contained in P, and I want to say that I2 is I want to check whether I2 is contained in P. So let us start with an element in, sorry, yeah, let us start with an element in I2. Now how do we think about a contradiction in this case, or how do we think about getting I1 is not in P? This implies that there exists some x in I1 but not in P. So now I have two elements x and y. What do we do with them?
Look at x plus y.
Yeah. So the first possibility is looking at x plus y. What can you say about x plus y? X is in I2, I1, y is in I2. So this is in I1 plus I2. That is not in our hands, right? It is little far from our. So what other possibility? xy. What can you say about xy? It is in I1 as well as in I2. So that means this is in the intersection, which means it is indeed in P. But if this is in P, one of them has to be in P. But there is one element which is not in P, x. X is not in P, therefore y belongs to P, and that is exactly we want to say, right. So therefore then xy is in I1 intersection I2, which is contained in P, and x is not in P, this implies y is in P. So this implies that I2 is contained in P. So therefore we proved if P is a prime ideal, and I1 comma I2 are ideals such that I1 P is contained in I1 intersection I2, sorry, P contains the I1 intersection I2, then P contains I1 or P contains I2, and the same is. So okay, looking at the proof, what if P is equal to I1 intersection I2? Can you say something more? If this were an equality, if P1 intersection P2, sorry, P is equal to I1 intersection I2.
I2 is contained in I.
So this, see, this will already say that this, right, equality means these both the inequalities are true. This inequality will imply that I1 is in P2 or I2 is in P2. This inequality implies that I1 contains P and I2 contains P. sorry, this is P. So, if I1 is contained in P, that would imply that I1 is equal to P. If I2 is contained in P, that would imply that I2 is equal to P. So, if P is equal to I1 intersection I2, then P is equal to I1 or P is equal to I2. These are some of the very important properties of prime ideals that we will one uses throughout study in commutative algebra. We will continue with more operations on ideals tomorrow.